Students, so here I am with my fourth video, and in this video we are going to discuss the preparation of haloalkanes. Okay, so to begin with, the first reaction is preparation from alkanes, and we know very well that alkanes can be halogenated in presence of sunlight and we get haloalkanes. So we have already done this in our previous class. Let us revise once again. For example, when methane is chlorinated in presence of sunlight, we get methyl chloride and HCl. It's a substitution reaction, and we know that substitution reactions are peculiar reactions of alkanes. Now, this methyl chloride can further undergo halogenation to form further substituted product like dichloromethane, trichloromethane, and even we can get tetrachloromethane. Carbon tetrachloride, organic solvent which is non-polar. Yes, so this is substitution reaction, and by substitution in presence of sunlight we get this. Dear children, the important mechanism is that free radical halogenation. It proceeds via the formation of free radical. We know a free radical is electrophilic in nature. Okay, so if you see that the tertiary alkyl group, where the tertiary free radical, if it is formed during the reaction, then that will be more stable, because the tertiary free radical, which is electron deficient, will be maximum stabilized by hyperconjugation or plus I effect. So tertiary is most stable free radical, then we have a secondary free radical, then the next stability is for primary free radical. So free radical substitution is maximum in tertiary alkanes, and then secondary, and then primary. So let us do the halogenation or chlorination of propane. So here we see that we have a 1 degree carbon atom here, 1 degree carbon atom here, and a 2 degree carbon atom here. So what are the possible products obtained here is CH3, CHCl, CH3, secondary substituted product, and we can also get CH3, CH2, CH2Cl. So of course the major product which we get here is secondary and minor, but you know children, around 45% we get primary and around 55% we get secondary. So major product is secondary only, because secondary free radical is more stable. Primary also we can see that there are more options here. There are 6 hydrogen atoms which are primary, and that could be the reason for 45% yield of primary. Now if we do iodination, like when methane is iodinated, we get methyl iodide and hydrogen iodide. Now this reaction is reversible. It's very important. Why it is reversible? What is the reason? This Hi is a strong reducing agent. So what it will do? It will reduce the CH3I and it will give back CH4 and I2. So this particular reaction, to get CH3I, what we can do? We can take a strong oxidizing agent in the reaction. For example, HiO3 hydroiodic acid, HNO3. These are the strong oxidants which will favor the reaction in forward direction. So in case of iodination, it's the reversible reaction, because Hi is a strong reducing agent and it can give back the reaction. So that's why we use a strong oxidizing agent. Moving on to next preparation, that is preparation from alkene. This is also very important, and this we did last year. Alkene, they undergo addition reaction And we know that when any halo acid is added to alkene, Markonicove's rule is followed, especially for unsymmetrical alkene, is significant. So if you just add to ethene HCl, there is no problem. We can just form a compound like this. Okay, the pi bond will break and we get a product like this. There's no problem, there's no tension here. But when we take unsymmetrical alkene like propene, and then when we add this HCl to this unsymmetrical propene, we know that here Markonicove's rule is formed. What is followed? Markonicove's rule is what? It says that negative part of the addendum goes to that carbon of the double bond which contains less number of hydrogen atom. Negative part of the addendum which is going to be added will go to that carbon atom of the double bond which contains less number of hydrogen atom. So we will follow the rule and we get a product like this. Okay, similarly, this Markonicove's rule can be followed in many cases. For example, let us take methyl cyclohexene. Let us add HBr, and here you see this is the carbon and this is the carbon-carbon double bond, and this particular carbon is a tertiary carbon where the number of hydrogen atoms are less. So definitely the negative part will go to this carbon and we get a product like this. Okay, so here no problem, we can follow the Markonicove's rule, but actual mechanism is what, children? It is electrophilic addition reaction. Electrophilic addition reaction. So what happens? Electrophilic addition means the formation of a carbocation is the rate determining step. Rate determining step, that is the slow step which determines the rate, and very important in reaction mechanisms. So what happens? Suppose we take CH3 double bond CH2, and when HCl is added, it proceeds via the formation of carbocation. So we can have here like this one carbocation, or we can have, if it shifts to here, another option, we will have a carbocation like this which is generated. Now look at this carbocation, which is again electrophilic, is more stable due to more hyperconjugation effect, and this particular carbocation is less stable because this side there is no alkyl group, so sp3s interaction is less. So this is more stable and this is the favorable product, and we get a product like this, two substituted product. So this is the mechanism. So it proceeds via the formation of carbocation. So definitely the tertiary group will favor the formation. So here secondary carbocation is formed. Let us take another important where we will learn something new. Let us take another example for this alkene addition. CH3CH, CH3CH double bond CH2. To this, if I add HBr, dear children, it's very easy. When you see that this particular carbon atom, according to Markonicove's rule, this particular carbon atom is having less number of hydrogen atom. So we can say that CH3CH, CH3, and write H like this, and then CHBr, CH3. My dear children, this product which is formed is as per Markonicove's rule, it's wrong. So how we can explain this? You see, if a carbocation is generated here, obviously as per the stability we can say that secondary carbocation is generated. Okay. Now this secondary carbocation, there is a scope that if you see the adjacent group, here one H is there, one methyl is there. So there is a hydride shift and the molecule rearranges by hydride shift. And why the molecule rearranges? to become more stable. So if there is a scope that adjacent atom can shift and can form a more stable carbocation, then it happens. So hydride will go here. Hydride is H minus. Hydride, that's why ide is there. Ide suffix is for negative ion, and it forms a tertiary carbocation here. So this is the tertiary carbocation which is generated, and we get a product. We get a product like this: CH3, C, CH3, Br, or if you are taking HBr, the Br, and CH2, CH3. Look at, this is a right product, this is a wrong product. So this is following Markonicove's rule, and this is as per the mechanism. So the mechanism is very important. It's electrophilic addition, molecule rearranges. If there is a methyl group, then methyl shift can happen. If there is a phenyl group, phenyl shift can happen. Okay, so order of preference is actually H minus shift maximum tendency, then pH minus, then methyl shift, like that it goes. So that is because of the shift, the carbocation which is generated is stable. So this is what we say, that electrophilic addition in alkenes. Thank you children. I'll come with next video and we'll discuss more preparations. Thank you.